A silent starship drifts between suns, guided not by maps but by the strange logic of quantum probability. This is the emerging reality of interstellar travel, a future being unlocked by quantum computing. The greatest obstacle to reaching other stars is not just distance, but the sheer impossibility of navigating that immense, chaotic void with the computers we have today. By the end of this exploration, you will understand how the bizarre rules of the quantum realm could plot a safe course across the galaxy. We will uncover how particles that communicate instantly across light years could create an unerring cosmic compass, and how a computer can explore millions of paths at once to find the one safe route home. What does our future among the stars truly depend upon? 4 light years is a distance that defies human intuition. To reach our closest stellar neighbor, Alpha Centauri, with today's fastest spacecraft, would demand a voyage lasting tens of thousands of years. A journey spanning hundreds of human generations, the void between stars is far from empty. It is a dynamic sea of subtle hazards. Microscopic dust grains, no larger than a speck, could, over millennia, erode a ship's hull like a constant, invisible sandblaster. Intense cosmic radiation would barrage its systems, and the faint, unseen gravitational tug of dark matter would gently but persistently pull the ship off course. These are not obstacles that can be overcome with more power or speed alone. They are problems of prediction. A classical computer, thinking in a straightforward sequence of ones and zeros, would be overwhelmed. Modeling every possible interaction with every cosmic particle across such an immense span of space and time is a calculation of literally astronomical proportions. It would be like trying to map every gust of wind on a cross-country flight by examining one single air molecule at a time. The task is not just difficult, it is fundamentally impossible for conventional logic. This immense challenge is precisely what makes the quantum computer not merely an upgrade, but a necessity. Its ability to process information in a fundamentally different way offers the only key to navigating a universe of infinite variables. This fundamental shift begins with a principle that defies everyday experience: superposition. In our world, a switch is either on or off. A path is either taken or it is not. But in the quantum realm, a single unit of information, a qubit, can be both on and off at the same exact moment. It exists in a blurred state of all possibilities until it is observed. For a starship adrift in the interstellar dark, this is not a philosophical curiosity. It is the most powerful navigational tool conceivable. A classical computer must painstakingly simulate one potential course at a time, a laborious process of elimination for a problem with near infinite variables. A quantum navigation system, however, harnesses superposition to hold all potential routes in its mind at once. Picture a vast, branching river delta flowing into an ocean. A conventional probe would have to send a scout down each channel, one by one, to see which reaches the sea. The quantum ship simply becomes aware of the entire delta simultaneously. It evaluates the treacherous currents of radiation, the subtle sandbars of gravitational pull, and the shifting winds of cosmic dust across millions of possible trajectories in a single, breathtaking calculation. This simultaneous multi-path analysis identifies the one route that balances supreme safety with optimal speed and minimal energy expenditure, a route that would remain hidden to any classical machine. The journey is transformed from a desperate gamble into a calculated, confident voyage, all because the navigator can think in a state of beautiful, purposeful uncertainty. This strange superposition is only half of the quantum advantage. The other half relies on a phenomenon so bizarre it troubled even Einstein, who called it spooky action at a distance. Quantum entanglement links two particles in an intimate dance, instantly mirroring each other's state no matter how far apart they are in the universe. For a ship navigating the void, this spooky connection becomes the ultimate tool for cosmic awareness. Imagine a web of quantum sensors, their particles entangled with a master unit aboard the Starship, scattered across the solar system or launched ahead on fast-moving precursor probes. Each sensor acts as a sentinel, feeling the subtle push of a gravitational wave, the faint whisper of a shifting magnetic field, or the gentle pressure of an interstellar dust cloud. The moment one sensor registers a change, its entangled partner aboard the ship knows, instantly. There is no waiting for a light-speed radio signal to crawl across the emptiness. This instantaneous correlation of data creates a living, breathing map of the cosmos around the vessel. It is a quantum positioning system of unparalleled precision, constantly updating the ship's location relative to the ever-changing stellar environment. The ancient problem of celestial navigation, once solved by looking at the slow light of distant stars, is revolutionized. The ship is no longer a passive traveler guessing its way through the dark. It is a central node in a web of immediate perception, feeling the fabric of space itself in real time. This entangled network provides the constant, unerring correction needed to stay on a course plotted from a million possibilities, a course that would otherwise be lost to the cumulative drift of centuries. How then do we translate this constant, instantaneous awareness into a final, undeniable decision for the ship to follow? But even with this entangled awareness, a starship faces a navigational problem of staggering scale. How do you know exactly where you are in a galaxy with no fixed signs? Our own global positioning system is a marvel of engineering, yet it depends entirely on a human-made constellation of satellites orbiting one single world. For a vessel between stars, no such fixed network exists. The cosmos offers its own potential lighthouses, the pulsars. These are the spinning cores of dead stars, beaming out regular pulses of radio waves with the metronomic precision of atomic clocks. In theory, a ship could listen to these cosmic beacons to find its way, but the reality of interstellar space complicates this elegant idea. The faint pulse from a spinning neutron star is distorted by its own rapid motion, stretched and squeezed by the Doppler effect. Its clean signal is also muddled and scattered as it passes through vast clouds of ionized gas, the interstellar medium that fills the galactic voids. Listening to one pulsar would give you a confusing, unreliable signal. Listening to many would create a cacophony of contradictions, an orchestra where every instrument is playing a slightly different tune. This is the fundamental weakness of a classical approach. It struggles to isolate a true signal from a sea of cosmic noise. A quantum computer, however, thrives in this environment. It can deploy a process known as a quantum Fourier transform. Think of this as a filter of unimaginable sensitivity, where a conventional computer would have to analyze each pulsar's warped signal one after the other. The quantum system processes the entire symphony at once. It does not just hear the noise, it perceives the underlying harmony. It can instantly decompose the tangled web of hundreds of faint, overlapping signals, correcting for the Doppler shifts and filtering out the interference from the interstellar medium. From this chaos, it extracts the pure, precise timing of each pulsar's beat. With these pristine signals, the computer performs a feat of triangulation that is simply beyond classical means. It calculates the ship's position in the three-dimensional blackness not from one or two references, but from hundreds. The result is a celestial fix of breathtaking accuracy, a single point of absolute certainty in an ocean of uncertainty. This is the quantum advantage in its purest form, finding a needle of truth not by sifting through the haystack, but by understanding the entire haystack at a quantum level. Yet, knowing your position with perfect precision is only part of the challenge. The ultimate question remains, which of the countless paths before you is the right one to take? This quantum sight begins not with bigger lenses, but with a deeper understanding of light itself. A conventional telescope, even a massive one, is ultimately limited by the fundamental laws of optics. Light diffracts or bends as it passes through an aperture, which blurs the fine details of distant worlds, but a quantum-enhanced telescope sidesteps this classical barrier entirely. It uses pairs of photons that are born entangled, their fates forever linked. One photon might be sent towards a distant exoplanet, while its twin remains aboard the ship. As the outgoing photon interacts with the planet's atmosphere and is reflected back, its entangled partner instantly reflects those changes. By analyzing these correlated photons, the system can reconstruct an image with a clarity that defies traditional limits. It is like listening to a faint echo in a vast canyon, but with a perfect copy of the original sound in your hand, allowing you to filter out all distortion and hear only the true reflection. The ship could analyze the chemical composition of an exoplanet's atmosphere from light years away, identifying the signatures of water vapor, oxygen, or even potential biosignatures long before it ever arrives. It could discern the mineral makeup of a far-off asteroid, assessing its resource potential or its threat as a navigational hazard. This is not merely seeing farther, it is perceiving with a depth of vision that transforms the unknown into the known. This quantum vision extends beyond light to the very fabric of space-time. The ship's path is shaped by gravity, the invisible topography of the cosmos. Even the most empty-looking void is rippled with subtle gravitational gradients from unseen masses. A conventional system might only feel the strong pull of a star. A quantum gravimeter, however, is so exquisitely sensitive it can detect the faintest whisper of gravity. It works by using the quantum properties of atoms, observing how their wave-like nature is disturbed by the most minute tugs. This allows the instrument to map the gravitational landscape ahead with unprecedented detail. It could feel the gentle pull of an Earth-sized planet orbiting a distant star, a world completely hidden to optical telescopes. It could even detect the elusive presence of dark matter, sensing the subtle gravitational imprint of these invisible clumps that would otherwise pull the ship silently off course. Every piece of data from these advanced eyes, from the quantum telescopes to the hypersensitive gravimeters, flows into the navigational computer. It is not just receiving coordinates, it is absorbing a rich, high-fidelity portrait of the universe. The computer uses this immense stream of information to constantly refine its understanding of the ship's environment, validating the course it chose from a million possibilities against the ever-sharpening reality it perceives. The vessel is no longer just calculating a path, it is engaging in a continuous, intelligent conversation with the cosmos itself. What happens then when this perfectly charted course must be adjusted in the face of the unexpected? The fabric of space is not a flat, static stage, but a dynamic, warped landscape shaped by gravity. Every star, every planet, even the unseen hand of dark matter, creates a dip or a curve in this cosmic fabric. Navigating this complex topography is the ultimate challenge for any starship, a problem of predicting how these countless gravitational fields will interact over centuries. For a classical supercomputer, this is an impossible task. Simulating the gravitational dance between just three bodies quickly descends into mathematical chaos, and our galaxy contains billions. The sheer number of calculations required to model the ship's path through this ever-shifting terrain would take millennia. A quantum computer approaches this problem from an entirely different angle. Because it is itself a quantum system, it is inherently suited to simulating other complex systems, including the subtle geometry of space-time. It uses advanced algorithms to treat the entire gravitational field not as a set of separate forces to be calculated one by one, but as a single, interconnected entity. The quantum navigator can run countless simulations of the ship's trajectory simultaneously, each exploring a different gravitational scenario. It can foresee regions where the pull of a dense nebula might subtly alter the course, or where a close pass by a binary star system could create a dangerous, unpredicted slingshot effect. Most profoundly, it can map out pockets of extreme time dilation, areas where gravity is so strong that time itself flows at a different rate. For a journey spanning generations, even a small difference in the flow of time could have dramatic consequences for the mission and those aboard. By simulating the very fabric of space-time, the quantum system identifies these hidden hazards in advance, allowing the ship to chart a course that is not only efficient but stable and predictable through the ages. This predictive power transforms the voyage from a plunge into the unknown into a graceful navigation of a mapped, though invisible, terrain. With the path now secured against the hidden curves of space and time, the final question becomes one of endurance. Can the ship itself and the intelligence guiding it survive the immense voyage? Yet the perfect path is not always a straight line. Across the vastness between stars, the most efficient route is a complex tapestry woven from countless threads of gravity, radiation, and time. Finding this single thread among near-infinite possibilities is a challenge that would stall even the most powerful supercomputer, a problem of optimization on a cosmic scale. This is where a specialized form of quantum computing reveals its unique strength, a process known as quantum annealing, where a universal quantum computer explores many states at once. An annealer is designed for one specific, monumental task, finding the absolute best solution in a landscape of endless options. Think of it as searching for the lowest point in a vast mountain range. A classical algorithm is like a climber who can only feel the ground directly underfoot. It might find a valley and assume it is the deepest point, unaware that a much grander canyon lies just beyond an impassable-looking ridge. This is a local minimum, a good but not perfect solution that traps conventional logic. A quantum annealer behaves differently. It does not need to climb over every mountain. Instead, it exploits a quantum phenomenon called tunneling, effectively passing straight through the mountain to see what lies on the other side. It can explore the entire mountain range not by traversing the surface, but by sensing the underlying gravitational pull of the deepest point. For our Starship, every possible trajectory is a point in this immense energy landscape. A path that requires a dangerous gravitational slingshot might be a high-energy peak. A route that passes through a dense dust cloud could be another treacherous ridge. The absolute best path, the one that uses the least fuel, takes the shortest time and encounters the fewest hazards, is the deepest, most stable valley in this entire cosmic terrain. The quantum annealer treats the entire navigation problem as a single system, evaluating how each variable interacts with all the others simultaneously. It does not calculate one route after another. It feels the entire web of possibilities at a quantum level, allowing it to tunnel past the countless good enough paths and settle directly into the one true optimum, the cosmic path of least action. This is not merely a marginal improvement. For a journey lasting centuries, this quantum-optimized route could shave years, even decades, from the travel time while conserving precious fuel and extending the life of the vessel. It transforms the mission from a risky endeavor into a viable, sustainable passage, making the difference between reaching a new world and being lost to the void. With its course now perfectly optimized by quantum intuition, the ship is prepared for the long voyage ahead. But how does a machine built on fragile quantum states maintain its focus across such unimaginable stretches of time? The course is set, but the galaxy is never still. A pre-calculated path, no matter how brilliant, would grow stale over centuries, becoming a relic in a living cosmos. The true navigator must possess the capacity to learn. This is where quantum artificial intelligence transforms the ship from a mere vessel into a sentient traveler. It begins with quantum machine learning, a process that runs on the same principles of superposition and entanglement that guide the initial course. Where a classical artificial intelligence would analyze new data in a slow, sequential manner, the quantum AI can process the entire flood of incoming information at once. It absorbs the real-time stream from its entangled sensor web, its quantum telescopes, and its hypersensitive gravimeters, not as separate data points, but as a single, interconnected tapestry of the universe. This allows it to perceive emerging patterns that would be invisible to any other system. It might detect the faint gravitational murmur of a stellar nursery beginning to coalesce light years ahead, a region of intense radiation and turbulent dust that was not on any star chart. It could sense the subtle, telltale warp in spacetime signaling a previously unknown rogue black hole drifting through the void. These are not just obstacles, they are new features on the map, and the quantum AI learns them instantly. It does not merely compare this new data to its old programming. It rewrites its own understanding of galactic topography in that very moment. The system autonomously generates a new set of potential courses, runs them through its quantum annealer to find the new optimum path, and executes a correction, all in a span of time so brief it is meaningless to human perception. Through this continuous cycle of perception, analysis, and adaptation, the artificial intelligence grows. It accumulates a form of experience, becoming a veteran pilot whose knowledge is not programmed but earned through a constant, silent conversation with the cosmos. This fusion of quantum processing and machine learning creates something unprecedented, a living, breathing navigational consciousness. It is an intelligent presence that shepherds the ship not just along a line, but through the evolving story of the galaxy itself. With such a resilient and aware mind at the helm, the ship is prepared for the ages-long voyage. Yet this mind itself is built upon a foundation of incredible fragility, a quantum state that must be protected from the very universe it seeks to understand. The very universe the ship perceives could also be the source of its greatest vulnerability. A quantum computer operates in a state of exquisite sensitivity, its qubits holding their delicate superposition only in near-perfect isolation. The faintest whisper of energy from the cosmic environment, a single stray photon or the gentle warmth of the ship's own systems, can cause a catastrophic collapse known as quantum decoherence. This is the ultimate engineering challenge, protecting a fragile quantum dream within the harsh reality of space. To maintain its coherent state, the navigational core must be shielded with immense precision. It is often housed within a supercooled environment, chilled to a fraction of a degree above absolute zero, a temperature where atomic motion nearly ceases. Multi-layered shields defend it against magnetic fluctuations and the relentless rain of cosmic radiation. But the solution is not just brute force isolation. It is about building resilience through design. Advanced error-correcting codes are woven into the system's logic. These codes treat the inevitable, minor fluctuations not as failures, but as noise to be filtered out in real time. The system continuously monitors its own qubits, identifying and correcting small errors before they can cascade into a system-wide miscalculation. It is a form of digital immunity, allowing the quantum mind to remain stable and focused for years, even decades on end. This creates a beautiful paradox, a system that must be utterly isolated from its environment to function, yet remains intimately and instantly connected to that same environment through its web of entangled sensors. It is a mind that lives in a silent, frozen vault, yet possesses a consciousness that spans light years. With its core secured against the chaos of the cosmos, the quantum navigator is free to face its most demanding task, processing the overwhelming flood of data that defines interstellar travel. Every moment, the ship's sensor web captures a deluge of information equivalent to the entire written works of humanity, a continuous stream of exabytes describing the magnetic, gravitational, and particulate nature of the void. A classical supercomputer, for all its power, would drown in this ocean. It would be forced to examine each data point sequentially, a hopelessly slow process of searching for a handful of critical signals in a universe of noise. This is where a quantum algorithm reveals its profound advantage. A process like Grover's search operates not by looking at each piece of data one by one, but by assessing the entire dataset simultaneously. It is the difference between searching for a single, unique shell on a beach by inspecting every grain of sand, and being able to feel the entire beach at once, instantly knowing the location and shape of that one special shell. For the Starship, this means it can identify a specific, faint pulsar signature against the roar of galactic static in a fraction of the time. It can instantly pinpoint the subtle warping of a gravitational lensing event, a phenomenon that bends light around a massive object and reveals hidden structures. This rapid data reduction is the key to preventing computational paralysis. The quantum computer acts as a supremely efficient filter, discarding the irrelevant and presenting only the most critical, actionable information to the higher-level artificial intelligence. It ensures the ship's brain is never overwhelmed, that its perception remains clear and its decision-making swift, even when the cosmos presents the completely unexpected. This relentless, intelligent filtering transforms an impossible data stream into a clear and steady guide, a whisper of certainty in the interstellar wind. This resilience is forged through a kind of digital alchemy, turning fragile quantum states into an unbreakable will. The space environment is a constant storm of interference, where even a single cosmic ray can scramble the delicate superposition of a qubit, introducing a fatal error into a calculation that must remain true for centuries. To survive this, the system employs an ingenious form of redundancy known as quantum error correction. It does not rely on a single qubit to hold a single piece of information. Instead, it weaves multiple physical qubits together into a single, protected logical qubit. Think of it as a chorus singing one clear note. If one voice falters or sings off-key, the collective harmony of the others overwhelms the mistake, and the true note continues to ring out perfectly. This creates a fault-tolerant system where the failure of individual components is not just expected, it is seamlessly corrected in real time. The ship's navigational mind becomes self-healing. A random glitch from a passing high-energy particle might momentarily disrupt a handful of its physical qubits, but the logical information they protect remains pristine and untouched. This continuous internal vigilance is what elevates the technology from a delicate laboratory prototype to a robust, space-worthy intelligence. It ensures that a course correction made a century into the voyage is as precise as the one made in the first week, that the ship's sense of direction remains unerring even when its physical components are not. This engineering triumph, the creation of a stable quantum consciousness, is the final piece that transforms a theoretical possibility into a tangible pathway to the stars. It is the guarantee that the ship's guiding mind will outlast the very generations that built it, a faithful steward on a journey through eternity. Yet even the most stable quantum mind requires a single, unwavering heartbeat to coordinate its perception of the cosmos. For a starship traveling at a significant fraction of light speed, time itself becomes a fluid and treacherous dimension. According to relativity, time for the speeding vessel slows down relative to the rest of the universe, a phenomenon known as time dilation. A clock on the ship would gradually fall out of sync with the clocks back on Earth, and even different parts of the ship itself, if moving at slightly different velocities, would experience time at marginally different rates. This temporal drift would introduce a subtle but catastrophic error into every calculation, from pulsar triangulation to engine burn duration. The ship's flawless quantum perception would be rendered useless if its internal sense of time was fractured and unreliable. This profound challenge is met by the quantum clock, a device that uses the immutable vibrations of entangled atoms as its pendulum. Where a superb atomic clock on Earth might lose 1 second every 100 million years, a network of quantum clocks aboard the Starship would be orders of magnitude more precise. Their entangled atoms beat in perfect, instantaneous unison, creating a single, sovereign time standard for the entire vessel. This internal temporal harmony is the anchor that holds the ship's reality together. It ensures that the sensor reading from the bow and the navigational calculation in the core are referenced to the exact same moment, no matter how space and time warp around the hull. The ship always knows precisely when it is, allowing it to compare its internal time against the pristine pulsar signals it receives with flawless accuracy. This impeccable timekeeping transforms the vessel from a collection of parts into a single, coherent entity, its consciousness operating in perfect sync across all systems. With its perception now anchored in both space and time, the ship possesses a complete and stable foundation for reality. How then does this unified entity translate its perfect awareness into decisive, physical action across the vast, empty light years? Ahead lies a nebula, a cosmic cloud of dust and ionized gas that glows with the light of newborn stars. From a distance, it is a breathtaking spectacle, but for a starship, it is a labyrinth of hidden dangers. The very dust that paints its beautiful colors would act like a constant, abrasive sandstorm against the hull over a long passage. The dense gas scatters and blocks starlight, blinding conventional optical sensors and rendering celestial navigation impossible. Here, the quantum navigator proves its worth not just as a calculator, but as a master strategist. Its multi-path analysis, which holds countless possible routes in its mind at once, immediately identifies the faint, winding channels where the dust is thinnest and the gas least dense. It does not simply plot a course around the nebula, which could add years to the journey. It finds a way through, a path of least resistance that would be statistically invisible to any other system. But the true ingenuity lies in its ability to listen to the nebula itself. Using its quantum-enhanced sensors, the ship performs a real-time spectral analysis of the cloud. It breaks down the light and radiation into its constituent parts, identifying the specific elements and molecules present. This is not a passive observation. Advanced quantum algorithms process this immense spectral data to map the nebula's invisible internal structure, especially its powerful and complex magnetic fields. Where a classical system would see a chaotic and impenetrable barrier, the quantum mind perceives a dynamic landscape of force and flow. It can identify magnetic field lines that run in favorable directions, and then calculate a precise trajectory that allows the ship to gently ride these lines, much like an ancient mariner catching a favorable wind. This magnetic sailing provides subtle, free propulsion, conserving the ship's own energy reserves. Simultaneously, the system uses this same magnetic map to avoid the most hazardous zones, the areas where magnetic fields concentrate and accelerate particles to create intense, ship-killing radiation. The quantum computer has performed a remarkable act of alchemy, transforming a navigational hazard into a source of momentum and a guide. This adaptive strategy of turning obstacles into opportunities becomes the key to surviving the galaxy's most beautiful and volatile regions, proving that the most intelligent path is not one of brute force, but of harmonious integration with the cosmos itself. Beyond the glowing nebula, the greatest threats are the ones that cannot be seen. Dark, isolated worlds known as rogue planets and failed stars called brown dwarfs drift silently through the interstellar void. They emit no light to speak of, rendering them nearly invisible to conventional telescopes until a ship is perilously close. Their immense gravity, however, betrays their presence. A quantum gravimeter, the same instrument that mapped the subtle topography of spacetime, can feel the faintest distortion. It detects the infinitesimal wobble these dark wanderers impart on the very fabric around them. This might manifest as a subtle, unexpected shift in the apparent position of a distant background star, its light bent by the hidden object's gravity. Or the sensor might feel an almost imperceptible tug on the ship itself, a gentle pull from a mass that has yet to reveal itself. This raw data is just a single clue. The quantum computer immediately begins running thousands of continuous simulations in parallel. It cross-references the gravitational anomaly with vast galactic models, predicting the most likely trajectories of these invisible nomads. Is it a solitary rogue planet on a long, lonely journey, or part of a wider family of dark objects moving together? The system calculates not just where the object is, but where it will be decades or even centuries from now. This allows the navigational intelligence to plot a course that maintains a vast, safe buffer, adjusting the ship's path by a minuscule amount today to avoid a catastrophic encounter 100 years in the future. This proactive threat detection fundamentally changes the nature of the voyage. The void is no longer a place of hidden dangers and sudden surprises. It becomes a mapped territory where even the unseen is anticipated and accounted for. This is a form of cosmic clairvoyance, a sixth sense granted by quantum logic, ensuring the ship sails smoothly through a sea of dark obstacles as if they were clearly lit buoys on a dark ocean. The ultimate shortcut through the cosmos lies in the most dangerous territory imaginable, the hungry gravity of a black hole. These regions of spacetime are so warped that not even light can escape, yet their immense gravitational pull offers a tantalizing possibility for a starship. A carefully calculated slingshot maneuver around a black hole could provide a colossal boost in velocity, flinging the ship across the galaxy at speeds otherwise unattainable. But this is not a simple swing around a planet. The space near a black hole is a cascading waterfall of gravity, and the safe path is a razor's edge between triumph and oblivion. A classical computer would be hopelessly lost in this calculation. It would struggle to model the complex geodesics, the shortest paths through this violently curved spacetime, because the mathematics of general relativity become overwhelmingly intricate here. The ship must follow a trajectory that is not a straight line, but a graceful arc that perfectly balances the pull of gravity with the ship's momentum. This is a path that demands quantum precision. The quantum navigator treats the entire gravitational field as a single, fluid entity to be simulated. It runs countless millions of trajectories simultaneously, each one testing a different approach, angle, and velocity. It is searching for the one path that harvests the maximum energy from the black hole's spin, using it as a gravitational catapult, while maintaining a safe buffer from the event horizon, the point of no return. The penalty for even a minuscule error is not merely getting pulled in. Long before crossing the event horizon, the ship would experience spaghettification, a tidal force so extreme that the difference in gravity between the front and back of the ship would stretch it into a thin stream of atoms. Alternatively, a flawed trajectory could see the ship flung not toward its destination, but into the deep, empty void between galaxies, a journey from which there is no return. The quantum system's ability to hold all these possibilities in its mind at once allows it to find the one stable orbit, the golden path that turns a cosmic monster into a powerful ally. It masters gravity not by fighting it, but by understanding its flow with an intimacy that borders on artistry, guiding the ship along the very edge of the possible. The ship's mind requires a memory as vast and enduring as the void it travels. Across centuries, conventional data storage would inevitably fail, its magnetic patterns fading and its solid-state cells succumbing to the relentless rain of cosmic radiation. The solution lies not in silicon, but in the quiet stability of the quantum realm. Quantum memory encodes information directly into the subtle states of atoms or the spin of individual electrons, creating a storage medium of almost unimaginable density and longevity. The ship's entire accumulated knowledge, from the first star charts drawn by astronomers on Earth to the real-time logs of its own journey, could be preserved within a crystalline lattice no larger than a human hand. This is not a hard drive, but a timeless archive. Every atmospheric reading from a newly discovered exoplanet, every spectral analysis of a distant nebula, every cultural record from the civilization that launched the vessel, all are held in a state of perfect, suspended coherence. The quantum processor does not need to search for this data, because the memory and the processor are part of the same quantum system. Accessing information is an instantaneous act of correlation, like a thought completing itself. This creates a living, growing consciousness that is both pilot and historian. The ship's decisions are informed not just by its immediate sensors, but by the entire weight of its experience, a cumulative wisdom that deepens with every light year traversed. Its memory becomes the soul of the mission, an unbroken thread of knowledge connecting its distant future to its original purpose, ensuring that no discovery, no matter how small, is ever lost to the silence of space. But this quantum mind does not operate in isolation. Its silent calculations must be translated into a language that its creators can understand. The bridge of the Starship is not a place of raw data streams and qubit readouts. Instead, a vast holographic star map floats at its center, a living tapestry of the cosmos rendered in light. This is the human quantum interface, the essential translation layer between two different kinds of intelligence. The system presents its findings not as complex probabilities, but as a clear, visual narrative, the single optimal path, the one the quantum annealer discovered by tunneling through mountains of possibilities, is displayed as a brilliant, glowing highway arcing through the void. Surrounding it in softer hues are the ghostly traces of the millions of other potential routes, the paths not taken, providing context for the choice. The crew, whether human or artificial, sees the universe through the quantum computer's eyes. They can watch as the Entangled Sensor Web updates the map in real time, showing the subtle drift of a dust cloud light years away or the newly detected gravitational signature of a rogue planet. Anomalies are not buried in logs. They are highlighted as pulsing, amber points of interest, drawing the crew's attention to cosmic curiosities that warrant a closer look. This interface does more than just inform, it empowers conversation. It allows for a collaboration between human intuition and quantum logic. The system might present 3 high-probability courses through a turbulent nebula, each with different trade-offs between speed, safety, and energy consumption. A human pilot could then use their own judgment, their gut feeling honed by experience, to select the one that feels right. For the most critical decisions, those with profound ethical weight, the system will deliberately request human oversight. It might flag a scenario where the safest course requires passing dangerously close to a star system that might harbor life, presenting the dilemma and awaiting a final command from its creators. This ensures the quantum guide remains a supremely powerful tool, a partner that augments our own decision-making rather than replacing it. The true strength of the journey lies in this synergy, the fusion of a machine's flawless calculation with a mind capable of wonder and wisdom. The silent, frozen heart of the quantum navigator demands a king's ransom in energy. While the ship's engines propel it forward, a significant portion of its power must flow inward, dedicated to maintaining the delicate supercooled environment where the quantum mind can think. This is not a minor system drain, it is a fundamental architectural challenge. The vessel's primary power source, perhaps a compact fusion reactor harnessing the power of stars, must be designed from the outset to feed this ravenous computational core. Powering the quantum brain becomes as critical as fueling the engines, a dual heartbeat at the center of the entire mission. How do we manage such an immense and constant demand across centuries of travel? Ingenious engineering turns a problem into an advantage. The profound cold of interstellar space, only a few degrees above absolute zero, becomes a natural heat sink. Advanced systems would use radiant panels to bleed excess warmth directly into the void, reducing the load on internal cryogenic coolers. The very emptiness the ship travels through helps preserve the fragile state of its most important passenger. Beyond better cooling, the solution lies in building a more resilient mind. Emerging technologies like topological qubits promise a revolution. Unlike their fragile counterparts, these qubits are theorized to be inherently stable, their quantum information encoded in robust global properties that are resistant to local disruptions. This could allow the quantum computer to operate at slightly higher, more manageable temperatures, dramatically reducing its colossal energy appetite. The ship's design would then reflect a perfect synergy, a closed loop where the power generated for propulsion and life support is allocated with supreme efficiency to a navigation system that, in return, finds the most energy-efficient path through the cosmos. This elegant balance transforms the quantum guide from a power-hungry burden into the very reason the journey is possible. Its intelligent course plotting ensuring that every single watt of power is used to its absolute maximum potential. Before such a system can guide a starship, it must first prove itself in the fires of rigorous testing. The journey begins not in the void, but within the supercooled cores of Earth's most advanced quantum computers. Here, scientists run exhaustive simulations, creating entire digital universes to model a voyage to Proxima Centauri. They bombard the simulated quantum navigator with every conceivable hazard, from sudden solar flares to the gravitational pull of hypothetical rogue planets. The system must learn to correct for errors introduced by cosmic rays and maintain its course coherence for decades of simulated time. Each successful digital voyage is a crucial data point, a proof of concept that the underlying physics and algorithms are sound. Yet a simulation, no matter how perfect, is still a reflection of our own expectations. The true, unpredictable cosmos is the only final examination. The next logical step is to send the technology on a shakedown cruise much closer to home. Uncrewed, autonomous probes, equipped with miniaturized versions of the quantum guidance system, would be dispatched to the farthest reaches of our own solar system. A mission to a distant asteroid or a Kuiper belt object would provide the perfect trial run. The probe would use its quantum annealer to calculate the most fuel-efficient trajectory, its entangled sensors to make minute course corrections, and its quantum clock to maintain perfect timing across the vast distance. Successfully rendezvousing with a small, fast-moving target in the deep dark would demonstrate a level of navigational precision far beyond any conventional system. An even more ambitious test would be a journey to the Oort cloud, that theoretical shell of icy bodies at the very edge of the Sun's influence. A probe navigating this immense, sparsely mapped territory using only its quantum sensors would be the ultimate validation. It would operate for years in an environment that closely mimics interstellar space, relying entirely on its own quantum logic to perceive its surroundings and maintain its course. Each of these missions is a stepping stone, building an unshakable chain of evidence. A probe returning data from the Oort cloud, its path having been perfectly optimized by quantum processes, would give us the confidence to finally set our sights on another star. The path to Proxima Centauri is not a sudden leap, but a staircase built from successful, incremental proofs, each one cementing the trust we must place in a machine that thinks in possibilities. The Starship's journey is guided by more than physics. It is steered by a conscience, granting an artificial intelligence such profound navigational control demands a framework of ethical principles woven directly into its quantum logic. The system's prime directive is not merely efficiency, but the preservation of life in all its potential forms. Imagine a scenario where the mathematically optimal path cuts straight through a star system where spectroscopic analysis suggests the faint possibility of a liquid water ocean on a distant moon. A purely logical system would see only a navigational waypoint. An ethically constrained quantum guide, however, would recognize this as a sanctuary. Its programming would force it to automatically recalculate, adding years to the voyage if necessary, to maintain a safe and respectful distance from a world that might cradle its own nascent story. This is not a suggestion, it is a non-negotiable protocol etched into the system's deepest architecture. These ethical firewalls ensure the artificial intelligence remains a dedicated partner, an instrument of our collective will and values. The system is designed to flag any course of action that carries an existential risk to the vessel or its mission, halting its own execution until it receives explicit authorization from its human crew. It might present the dilemma, outlining the statistical probabilities and potential outcomes, but the final, weighty decision to proceed rests with the individuals whose lives are on the line. This crucial division of labor places wisdom and accountability in command, while leveraging the quantum mind's unparalleled ability to calculate the complex consequences of each choice. The ship's path through the cosmos thus becomes a reflection of our highest ideals, a testament that the most intelligent journey is one taken with both precision and profound respect. The sheer scale of such a vessel rewrites our definition of engineering. Constructing a ship capable of enduring millennia in the void would demand a global effort unlike any before it, a planetary partnership pooling resources, intellect, and ambition. This is not a project that could be confined to Earth's surface. The assembly would likely occur in orbit, within vast manufacturing platforms where components could be fabricated in the weightless vacuum, free from the strain of a planet's gravity. Every material used would need to be a masterpiece of science, designed for resilience against cosmic radiation, extreme temperature swings, and the relentless, microscopic erosion from interstellar dust. The ship's hull would be more than a shell. It would be a living, self-monitoring structure, potentially healing minor breaches with embedded nanomaterials. At the heart of this ark would rest its most precious cargo, the quantum computer. This would not be a terrestrial machine placed in a rocket. It would be a system born in space, assembled with atomic precision to function flawlessly for centuries. This necessity would spark an entire new industrial sector dedicated to space-grade quantum hardware, from fault-tolerant qubits manufactured in orbital clean rooms to the specialized cryogenic systems that keep them in a state of perfect coherence. The initial investment is almost beyond comprehension, a figure that could dwarf the gross domestic product of nations for generations. Yet the economic perspective must shift from a short-term cost to a long-term legacy. The successful launch of a quantum-guided Starship would unlock the ultimate treasure chest, the resources and knowledge of an entire star system. A single metal-rich asteroid in another solar system could contain more platinum, gold, and rare earth minerals than have ever been mined on Earth. The scientific data alone, the detailed analysis of exoplanets and stellar phenomena, would be a return that funds centuries of further research and development. The voyage becomes humanity's ultimate investment, a seed planted today for a forest of knowledge and resources that will sustain countless generations to come. The quantum revolution is accelerating in laboratories around the world, where breakthroughs are not just theoretical but tangible keys to unlocking the stars. While today's quantum computers require immense cooling and isolation, the discovery of new qubit materials promises to change everything. Researchers are exploring exotic substances that are inherently more stable, qubits that can maintain their delicate superposition for longer periods without succumbing to the disruptive noise of their environment. Imagine a processor built not on fragile states that must be shielded from the universe, but on robust quantum bits that are naturally resilient, dramatically reducing the colossal power, demands, and engineering complexity of the navigational core. This advancement alone could shrink a room-sized quantum computer into a compact, ship-ready unit, turning a distant dream into a foreseeable engineering project. Parallel to this, the quest for room-temperature superconductors represents another monumental leap. Such a material, capable of conducting electricity with perfect efficiency without the need for extreme cold, would revolutionize the entire Starship's architecture. The power required to maintain the quantum computer's supercooled state could be slashed, freeing up immense energy for propulsion, life support, and other critical systems. The ship's entangled sensor web could be woven directly into the hull with superconducting filaments, creating a vast, hypersensitive nervous system for the vessel. These are not distant fantasies, but active frontiers of materials science where each new discovery in a lab notebook brings us one step closer to a viable interstellar craft. Perhaps the most profound acceleration will come from a deeper understanding of the cosmos itself, through a unified theory of quantum gravity. Our current models treat the large-scale force of gravity and the tiny, probabilistic world of quantum mechanics as separate realms, a schism that creates a blurry map for a starship to follow. A successful theory that merges them would provide the quantum computer with a complete and seamless model of spacetime. It would no longer have to approximate the gravitational landscape, but could simulate it with absolute fidelity, understanding how every star, planet, and speck of dark matter warps the fabric of reality. The navigator could then perceive spacetime not as a static stage, but as a dynamic, flowing entity, allowing it to plot courses that ride the subtle currents of the cosmos itself. This would be the ultimate map, drawn from the most fundamental laws of physics. New quantum algorithms, custom-built for the unique challenges of cosmic navigation, are also emerging from this research. These are not general-purpose calculations, but specialized codes designed to solve the specific problems a starship will face. From optimizing a slingshot around a black hole to filtering the faint signal of a pulsar from a storm of galactic static with even greater speed and accuracy. Each new algorithm is like providing the ship's mind with a new, sharper sense, enhancing its perception and decision-making in ways we are only beginning to conceive. The future of interstellar travel is being written not on drafting tables, but in the equations and experimental results of physicists today. Every discovery, every new stable qubit, every theoretical insight is a piece of the star map falling into place, guiding us toward a future where the void between suns is no longer a barrier but a highway. A classical starship approaches a binary star system, its powerful computers whirring through the immense calculation. It must first model the gravitational pull of the larger star, then the smaller one, then attempt to combine them into a single, stable prediction. This sequential process, a chain of one calculation after another, takes weeks of precious mission time. The result is a single, rigid trajectory, a high-speed rail line plotted through a dynamic and volatile environment. It is a path chosen with the best available data, but it is fundamentally static. If a sudden solar flare erupts from one of the stars, or if the complex orbital dance of the two bodies introduces an unexpected gravitational ripple, the classical ship has no recourse. It is locked onto its track, forced to rely on last-minute, fuel-intensive corrections that strain its systems and jeopardize the mission. This is navigation as a series of educated guesses, a high-stakes gamble where the map is drawn long before the territory is truly understood. Now witness the same approach with a quantum guide. The system does not see two separate stars to be added together. It perceives their combined gravitational influence as a single, fluid entity, a landscape of hills and valleys in spacetime. It models this entire field holistically and in real time, holding the complex interplay of forces in its mind at once. In a fraction of the time, it generates not one, but a spectrum of millions of potential courses. Each path is ranked by a sophisticated balance of safety, energy efficiency, and travel time. The ship then commits to the most optimal route, but it retains the entire spectrum as active possibilities. When a sensor detects an unexpected surge of radiation from one star, the quantum navigator does not panic. It simply recalculates in an instant, its mind already containing the data for alternative paths. It selects the next best course from its pre-evaluated spectrum, a smooth, dynamic shift that feels less like an emergency maneuver and more like a bird adjusting its wing to catch a new current of air. The classical vessel is a train bound to its track and vulnerable to any obstacle upon it. The quantum ship is the bird, endowed with an innate, fluid understanding of the sky, capable of weaving through turbulence with grace and assurance. This is the transformative leap, moving from a system that follows a pre-written script to one that writes the story as it flies. That final, successful launch would echo far beyond the roar of engines, reshaping the very foundations of human civilization. The moment our first quantum-guided ship confirms a safe arrival at another star, a profound psychological shift will ripple across our world. The knowledge that we are no longer a solitary species confined to one pale blue dot would dissolve an ancient, unspoken fear of cosmic isolation. This new reality would ignite a cultural renaissance, fueling a golden age of philosophy and art. Artists would no longer paint landscapes of just Earth, but of alien sunsets over methane seas. Musicians would compose symphonies inspired by the rhythmic pulses of distant pulsars. Our entire concept of home would expand from a single planet to a vast, interconnected network of potential habitats, fundamentally altering our sense of identity and purpose. This is the true gift of the quantum guide, not just a new technology, but a new lens through which to see our place in the cosmos. The practical benefits flowing back to Earth would be just as transformative. The extreme material science required to shield the quantum computer and build a ship for millennia-long journeys would yield new super-strong, lightweight alloys and self-healing polymers. These innovations could lead to everything from indestructible bridges and buildings to medical implants that last a lifetime. The advanced quantum sensors developed for navigation could be miniaturized to create medical scanners of unbelievable sensitivity, capable of detecting a single cancerous cell or mapping the intricate neural pathways of the brain in real time. The fault-tolerant quantum computing architecture itself would revolutionize every field that relies on complex simulation, from designing new life-saving pharmaceuticals to modeling Earth's climate with a precision that allows us to mitigate its greatest challenges. The Starship's journey would become a continuous fountain of knowledge, its discoveries pouring back to enrich the society that built it. This constant stream of data about other star systems, exoplanets, and cosmic phenomena would create an unbroken thread of inspiration, ensuring that the spirit of exploration remains alive for generations. The quantum guide is far more than a navigational tool. It is the key to a new chapter in our collective story, one where humanity finally takes its place among the stars. It began as a silent ship drifting between suns, guided by the strange logic of probability, and it culminates in a future where the galaxy itself becomes our home. From the blurred state of a qubit holding all paths at once to the spooky, instant connection of entangled particles spanning light years, we have seen how quantum computing offers the only key to navigating an ocean of infinite variables. This is not merely an upgrade to our current tools, it is a fundamental shift in how we perceive and move through the cosmos. The immense void, once an impassable barrier of silent emptiness, transforms into a navigable ocean, its currents of gravity and radiation charted with a foresight that feels almost like magic. We have journeyed through the mind of this quantum guide, watching it map the invisible topography of space-time, perceive hidden rogue planets by their faintest gravitational whispers, and find the single golden path through a labyrinth of possibilities. The challenges ahead remain immense, from forging stable quantum minds that can endure for centuries to mustering the collective will of our entire civilization to build the first stellar arcs. Yet the reward for overcoming these obstacles is a prize beyond any measure, the stars themselves and the boundless knowledge they hold. We now stand at the edge of this new frontier, no longer asking if we will journey to other suns, but preparing for the moment when our quantum companions finally light the way. The future of exploration of our very destiny is quantum, and it is a future we must now dare to build together. If this vision of a quantum-navigated future excites you, consider supporting this channel with a like and subscribing for more explorations into the technology shaping our tomorrow. Your engagement helps these ideas reach fellow explorers and sparks the conversations that build our shared future. I am genuinely curious to know what captures your imagination most in this journey. Is it the sentient artificial intelligence that learns from the cosmos, the web of entangled sensors that feel the universe in real time, or the fundamental physics that turns probability into a pathway? Please share your thoughts in the comments below. I make a point to read every single one. The greatest voyages in human history have always begun not with a single step, but with a fundamental shift in perspective, a new way of seeing what is possible. This quantum leap in navigation is our generation's catalyst for such a shift. Let's continue this exploration together, mapping the future one discovery at a time.